Okay, yes, in last class, suddenly the Meet was stopped. I think I did not notice. After after 8 p.m., was asking about any question. Then I saw that it was disconnected. Okay, so if in same thing happens today also, probably it will not happen. In last class, it was happened due to some network issue probably. If happens today, then you can message me so that I can increase it. Because when I am sharing the screen from my tab, then I can't show the meeting process. So that's why I did not notice. Okay, so let us start. Let me set the screen. Right. So is it visible now?
Yes, yes.
Okay, so you send me 10 or 11 questions, so we'll discuss today that. But first, we'll discuss some, as I stated yesterday in last class, not yesterday, that we'll first discuss about some numerical question about the biological theory or ionic strength, those things. Then after that, we'll discuss the questions you have sent me. Mm, mm, Okay, and then we'll solve some question from classes taught in this week, especially on statistical thermodynamics that was introduced in last week. Okay, so first question. Let us start. Okay, first I'm writing the question, then I'll solve. Calculate the ionic strength of 0.15 molar potassium chloride solution. Second, 0.25 molar K2SO4 solution. Third one is 0.2 molar BaCl2 solution. Fourth one, solution in which 0.1 molar KCl is there and 0.2 molar K2SO4. So there are four solutions is provided and we have to find out the ionic strength for each solution. Okay. So what was ionic strength? ionic strength is denoted by I, that is defined as like this. That is half into sum over Ci Zi square, sum over I. So what is Ci and what is Zi here? Zi is the charge of ith ion and Ci is the concentration of ith ion. Okay. So we have to follow this definition, then we can easily mm, I, easily calculate the strength, ionic strength. Okay. So first one is 0.15 molar KCl. Okay, first one thing, what is molar? Because probably we have already studied that molarity, molality, normality, these things are, but molarity and molality, these two things are different. Both are used for defining any solution, concentration of solution. So we know that solution means there is solvent, and in solvent we are adding some solute. Solute means the uh, less quantity. Solute has a less quantity and solvent has a more quantity. So that's why we can identify solute and solvent. It's now by using molarity or molality or normality, using these terms, we can identify how much solute is dissolved in the solvent. Okay. So the definition of molarity is, let's say, if there is one or x mole solute is dissolved in 1000 ml of solution, then it is called x molar. So here important thing is solution. Okay, so x mole solute is dissolved in 1000 ml of solution. But in case of molality, we basically use the kg. Means that, let me define. Okay, that is molar. Now if molar, in case of molar, it is like molar if x kg solute is dissolved okay uh, in 1000 ml of solvent. Okay, so then it is called x molar. So both are not equal. For molar, it is just x mole, but here it is x kg. Okay, so there is difference. So we have to keep in mind that the molarity or molarity is not same. But in case of ionic strength, we basically use, in general, we use as molality. Both are concentration, molarity, and these concentration are, we can change from molarity to molarity or normality. So these are interchangeable. But here, basically, in case of ionic strength, we basically deal with the molality. Okay. So if there is if nothing is mentioned there, then generality is, it is considered the molality is given. So now let us focus our problem first. What was the problem? 0.15 molal KCl. It is mentioned here that it is molal. So nothing to worry. 0.15 molal KCl. How KCl dissolves? That's K plus and Cl minus. So there are two ions. One is anion, another one is cation. So now what will be ionic strength? It will be essentially half into Ci square. So half into concentration of K plus, charge of K plus square plus concentration of Cl minus charge of Cl minus square. Okay, so both are 1. Okay,
Explanation.
yes,
The explanation.
yes,
The formula of molarity,
formula,
as far as my
formula.
knowledge is concerned, molar,
Uh-huh.
MOLAL.
Yes.
As far as my knowledge is concerned, it is something X mole per 1,000 gram or 1 kg.
Please repeat. Repeat. Okay, okay.
The molarity means
I understand. Understand.
something in
Okay, okay, okay.
something gram.
This you want to say, no? Okay.
Yes, yes.
Mm. So it was interchange. Okay. So in both case it is x mole. It should be, but here it is in first case it's 1,000 ml. Here 1,000 kg. Okay. But here it is solution. Here it is solvent. These things also we have to keep in mind. Okay. Thank you. For water these are equal. Okay, so it's very trivial because in case of water it's 1 the density, so that's why it does not matter so much, but for other solvent it's very important. Okay, so here it is ck plus 1 square ccl minus 1 square, so it is half into ck plus ccl minus. Yes, so now we have to find out the concentration. So what was the leakage? kcl dissociate in K plus and Cl minus. If the concentration of KCl is X, let's say, then obviously the concentration of K plus and Cl minus will be the X, because one KCl molecule uh, dissociate into one K plus ion and one Cl minus ion. So if there X number of molecules are there, let's say, so then X number of K plus ion will be generated and X number of Cl minus ion will be generated. Okay, hence the concentration will be same for K plus and Cl minus, and that will be equals to KCl. Okay. Now, what is the concentration of KCl? That is 0.15 molar. So, essentially, the concentration for our K plus and Cl minus will also be 0.15 mole. So, just if you write it, then it will be 2 into 0.15. So, it is 0.15. Okay. So, ionic strength is 0.15. So, these things is very important. Just this part. Thanks for the correction. It was my. Hmm. Okay. Now, what is the second question? Now, it is also we have to solve similarly. The second question is in the 0.25 molar K2SO4. So K2SO4 essentially dissolve in 2K plus SO4 2 minus. Two ions are there. So if it is concentration of K2SO4 was X, then obviously the concentration of K plus will be 2x and SO4 will be X. Okay. So now I will be half into C of just plus for cation I'm writing Zi square, so which is plus 1 square plus C minus 2 square. So it will be half. What is C plus? That is 2x. 1 square is 1 and C minus is x and it is 4. So it will be 3x. So now what is x? X is the concentration of K2SO4 in molal. So X is eventually that is given 0.25. So it will be 0.75. Okay, straightforward. Now the third question, it will be also solved similarly. That 0.2 molar BaCl2 solution they have asked. Barium chloride. So it will be again this is Ba2 plus and 2 Cl minus. So similarly, we can write that if the concentration of BaCl2 is X, then obviously the concentration of Ba2 plus will be X, and for Cl minus it will be 2X. So I will be half C plus 2 square plus C minus 1 square. So eventually it will be 4X because C plus is X and C minus is 2X. So it is 2X. So again it is 3X. Now the X is here given 0.2. So it is 0.6. Okay. Now the last one. Okay, it's important. What given the solution which is 0.1 molar in KCl and 0.2 molar in K2SO4. So there are eventually two salts are dissolved. So first one is generating K plus and Cl minus, and second one is also generating K plus, but anion is different, so for 2 minus. So eventually we can write from KCl plus K2SO4 we are having 3K plus and 1 Cl minus 1 SO4 2 minus. Okay, so let us start with concentration of X. KCl is X and for K2SO4 is Y. Then what will be the concentration of K plus? So we can think like that this is just K plus 2K plus. This K plus is coming from KCl, then obviously this concentration will be X. The concentration, this is coming from the K2SO4, so this will be 2Y. Cl minus is coming from KCl, so this will be X, and this O2 minus is coming from K2SO4, so this will be the concentration. Okay, so now still you can write the concentration of K plus should be X plus 2Y. Concentration of Cl minus will be X, and concentration of SO2 minus will be Y. Now we can calculate the I, that is half of sum over Ci Zi square. So we can write half of, now specifically you have to write Ck plus Zk plus square plus C Cl minus ZCl minus square plus CSO4 2 minus ZSO4 2 minus square. So it will be half into Ck plus, what is Ck plus? X plus 2y, and Zk plus is 1 square, it is X minus 1 square, it is Y into minus 2 square. Okay, so half into X plus 2y plus X plus 4y. So it is eventually X plus 3y. Now the X and Y. X is the concentration of KCl, which is given as 0.1, and Y is concentration of K2SO4, and that is given as 0.2. So eventually you can write it 0.1 plus 0.6, so it should be 0.7. So this is the general case where if there is more than 2 or 3 or 4, any number of solution can be there, number salt can be dissolved there, so multiple types of ions will be present, but the formula will be same. Okay, so now the question number 2. Okay, First, let me write it, then we'll discuss. Solution, solutions of three electrolytes have the same ionic strength and different dielectric constant as that is given 4, 25 and 81, and expected temperature is 5 Kelvin, 256 Kelvin and 298 Kelvin. The corresponding relative magnitude of the bifocal Screening lengths of the three solutions. Okay. So three, solutions of three electrolytes are given, the same ionic strength, and different dielectric constant. For three solutions, dielectric constant of 4, 25, and 81. And temperature is also given. For first solution, it is 225 Kelvin. For second solution, it is 256 Kelvin, and for third solution is 298 Kelvin. Now, they have asked the relative magnitude of Debye spinning length. So Debye spinning length, we have to identify the relative magnitude, that is the ratio for these three solutions. Let's find it out. So for that, we need to know what is the Debye spinning length. So Debye spinning length is basically denoted by kappa, which is defined as 2 p square Na. Okay, no. Divided is kappa inverse, and kappa is 2 square Na I divided by epsilon kBt. Okay, so to the power half. This is kappa. So now what is then divided string then, that we can write also Rd. So Rd will be kappa inverse. So that will be 2 square NaI epsilon kBt to the power minus, or epsilon kBt divided by 2 square NaI to the power half. Okay, so this is the Debye string length. Why this is called Debye string length? Because if you notice the detailed derivation of Debye limiting law, then around a central ion, mm, let's say if it is a positively charged ion, cation, then around the central ion there will be a uh, cloud of negatively charged ions. So like this, you can think there will be a cloud of negatively charged ion or anions. So like this. Okay, but the concentration of, let's say if this is, okay, so let's say if this is the radius r, that means the distance of the negatively charged ion from the central cation, then if you plot the concentration of the negatively charged ion with the distance, then it will passes through a maximum. So around that maxima, the density of the negatively charged ion is maximum. So that length is basically RD, the Debye spinning length, and that is equals to kappa inverse. If you look at the details derivation, you can identify this. Okay, so RD, we know RD, but if you look at the expression of RD, here everything is constant. Not everything, KB is constant. KB is constant. Na is Avogadro number, that is constant. E is electric charge of electrons, that is also constant. So depending on the solution, if you change the solution, then obviously epsilon will change, temperature can be changed, and ionic strength can also be changed. So eventually now for our cases, R1, we know R1, R2, or RD1, RD2, RD3, three electrolytes are given, electrolyte solution are given. For all cases, I is same, ionic strength are equal. That is given. That means I is same. So eventually, now we can write it that for our cases, for this problem, R is only proportional to epsilon is there, and epsilon and P. Rest are the constant. So epsilon and P, that can vary. Okay, so epsilon and P will be changed. Now what is epsilon? Epsilon is dielectric constant of the medium. So epsilon R, that is relative permeability. So that is defined as, we know, epsilon divided by epsilon naught. Epsilon naught is the permeability in the vacuum. So we can write it. So R can be written as permeability or permittivity. Let's check the right term. Yes, not permeability, it's permittivity. So it will be epsilon naught, epsilon R, T to the power half. Okay. So that is not important here even. Okay. Okay, now on epsilon R is dielectric constant or relative permittivity, you can say both. Both are the same thing, and that is defined as epsilon by epsilon naught. So now you can write that R is eventually proportional to epsilon R T to the power half. Because epsilon naught is constant, this is for vacuum. Permittivity of vacuum. Okay. So this is now given. So eventually R1 is to R, not R, RD1 is RD2 is to RD3. That will be epsilon R for 1, P for 1 is to epsilon R for 2, T2, and epsilon R 3, T3. So now these things are given in the question. Epsilon R1, what is epsilon R1? 4, and T1 is 2 to 5. So this is 4 into 2 to 5 is to epsilon R2 is 25 and T2 is 256. So this is 25 into 256. For the third one, it is 81 and 298. 81 to 98 to the power half. Okay. So now we have to just find it out. If t is 225 into 4 divided 225 times is the next one is 2 into 2 5 6 HP is 80. For the last one is 81 into 298. It is 155.36. So this is all the ratios. Okay. So this is very important equation. Let me again write it. It is already written. So this equation is very important. Okay. Now question number 3. Again the dielectric constant is given. Salt AB and A2B is 100 and 121. If the concentration of AB is 0.01 molar and that of A2B is 0.02 molar, then the relation between the device string length, that means RD, at the same temperature. There are 4 options. First one is K of is kappa of AB inverse equals to kappa of A2B inverse. Second option is kappa of AB inverse is greater than kappa of A2B inverse. Third option is kappa of AB inverse is less than kappa of A2B inverse. The fourth one is can't be predicted. Okay. So now we have to again find out. So here we have to remind it that concentration are given in molar, not in molar. So that does not matter. We can also delete the molar. Okay. So now if we know that RD is the kappa inverse, that is important. That's why everywhere it is written as kappa inverse. Okay. So kappa inverse is eventually, we know that is epsilon r to epsilon naught. If you look at the equation, epsilon is basically epsilon r into epsilon naught into kBt divided 2 square NaI to the power half. Okay. So again, the constant terms are, because both are in the same temperature here. So constant will be, E will be constant, Kb is eventually constant, epsilon not constant, E constant, Na constant. So these are constant. So you can write Rd or kappa inverse is proportional to epsilon r by I to the power half. Okay. So now we have to find out the I1 and I2, IAB and IB, A2B. So IAB sum over ci z I square. Let me give you specific. So it is ca plus za plus square plus cb minus zb minus square. So how ab will dissolve a plus and b minus. So za plus and zb minus both are 1. Okay, and the concentration of ab, if it is x, as I discussed earlier, that it will be also x. A plus and b minus both will be x, so we can write it as x za plus is basically 1 square plus x into minus 1 square. So it is x, and it is given 0.01 in mole, obviously. So let me write in mole. Okay, a to b. So in a similar note, you can write it a plus za plus okay. Here how a to b will dissolve, that a to b 2a plus b2 minus. So if it is x, then it will be, or let's say for it's y, so then it's 2y, this will be y. So half of 2y, and what is the charge? 1, so it is 1 square. This is cb2 minus, this is y, and charge is minus 2 square. So half of 3y. So it is 3 into what is y? Y is 0.02. So 0.06 molar. Okay. So what will be the RD AB, that will be proportional to epsilon R of AB divided by I. I is 0.01 to the power half, and RD A to B, that will proportional to epsilon R A to B divided by 0.06 to the power half. Okay, so we can write it as this is 100 into epsilon R. Epsilon R, okay, epsilon R, this is 600. Okay, so it is given that epsilon R, and this is given, I think, yes, 100 and 121. So you can write it 100 into 100 to the power half, and this is 600 into 121 to the power half. Okay, so it's clear that RD1 is small than RD2. RD1 to 1 to it's AB, it's A to B, because it's 100 into 100, it's 600 into 121. So that means kappa inverse for AB is smaller than kappa inverse for A. Check if there's mistake. Yes, it's correct. Okay. So now by I. Yes. No, so it's correct. I see 600 121 is primary to be sometimes. The answer is not matching. Yeah, like
It is
this one.
matching with
Yes. Is there any
it is
mistake?
matching with no, it is matching with option 3.
It's matching in option 3, but in the answer sheet it is given as option B. That means the reverse one. Let me check. Wait, let me doing this way. Yes, this is correct. I think 100 0.1 to the power half. Okay. Okay, no, no, not it is. It is 1.1 divided by 16, 0.06 to the power half. Now, if we take the ratio RGB divided by, then it will be so now is 600 121 to the power half. Okay, okay, no, there I have done mistake, right? Yes. 0 point, it is 0.06 of 0.06 means 6 by 100, not 600. So it is eventually this. Okay, so then it is correct. But let me do in this way. So it is this. So 121. This is, if you take root, so it is eventually 2.2. So from here explicitly we can write. So it's better to do in this way. Then there will be no chance to make any wrong. This is so now it's clear. Okay, so that means kappa inverse of AB is greater than kappa inverse of AB. So eventually it should be option B. Okay, so let me check if there any question left or not. Yes, last question is there. Then we'll discuss the assignment question. Question number 4. Calculate the mean activity coefficient of NaCl, the molality 0.01, Na2SO4 at a molality of 0.001 in aqueous solution at 25 degrees centigrade. Okay, so they have asked the mean activity coefficient of NaCl and Na2SO4. Okay, so what was the mean activity coefficient that we have to know? That is gamma. In last class we discussed mean ionic activity coefficient, that is gamma plus minus this was mean ionic activity coefficient, or so again a plus minus 1 was mean ionic activity, and this is, so how was the relation? This was related to this mm, activity coefficient into concentration, like this. So we have to find out the mean ionic activity coefficient. That is eventually the gamma plus minus. So, and gamma is the total ionic activity coefficient, that is gamma plus minus to the power nu. So nu is nu. Nu is actually nu plus nu minus total number of ions. So this thing we have discussed already. Now how we can find out the gamma plus minus? That is uh, evaluated using the Debye limiting law. Debye limiting law, what does it say? That log of gamma plus minus is minus a z plus z minus into root over r. Okay, so this is our equation for the, there is a limitation for very dilute solution, because there was a denominator, we have uh, we have omitted that part, approximated, considering very dilute solution, then only the numerator will left, and this will be reduces to a into z plus z minus into root over I. So now we have to find out gamma plus minus. So for that we have to go through like this. First one is, what is NaCl? 0.01 molar NaCl. So eventually we have to find it out. I, Z plus Z minus, we know, and A. What is A? A has a big expression, we know. But here one thing is mentioned, that is the 25 degree. So at 25 degree for aqueous solution, for aqueous solution at 298 Kelvin, A has a very specific value, that is 0.509. So we have to remember this value, because if this condition is given, aqueous solution and 25 degree, then it will not be provided. This value you have to keep in mind always. So that's why it is not provided in the question. So 0.0, now it's easy. Now everything is known. You have to just find out I. That will be sum over I Ciz square up into C of Na plus Z of Na plus square plus C of Cl minus Z of Cl minus square. So it will be half of, what is C of Na plus? Okay, so NaCl will dissolve like Na plus and Cl minus. So if the concentration of NaCl is X, then it will be also X and X. So it is X 1 square. So it's X. What is X? 0.01 molar. So 0.01 I is now known. So it's now trivial to find out what will be the log of it. So it is minus 0.509 into, what is Z plus? It is 1. What is Z minus? It is minus 1, and root over I, that is 0.01. So it will be 509 into 1 into 1 into root over 0.01. So it is okay. One thing on there is a mod. So it is again 0.509, 0.510. Okay. So if this is the case, then what will be the log plus minus? It will be because it's 10 base, so we can find out. So it will be 0.889. Okay. So this is the mean earning activity coefficient for the NaCl solution. Now the second question for the Na2SO4 solution. How Na2SO4 will dissolve? 2 Na plus and 1 SO4 2 minus. So let if the concentration of Na2SO4 is x, then obviously the concentration of Na plus will be 2x and this is x. So I will be again sum over Ci zeta square. So half and the concentration x is given 0.001 molar. So what is the z plus 1? What is the z minus 2? But there is a mod. So it is not 0.003. So 0.000558. So then it's FM. So this is the mean earning activity coefficient. Okay. So probably now, yes. Now we'll solve the assignment questions. Okay. So first problem you have sent me that 1 mole of an ideal gas expands from in atmospheric pressure in ATM against a constant pressure of 1 atm at 27 degrees centigrade. Now the magnitude of work done by the gas. Right, this we have to find out. So first, this is ideal gas, and this is expanding from 10 atmospheric pressure to 1 atmospheric pressure. Okay, at 27 degrees centigrade, and the magnitude of work done. Okay, and this is isothermal process. We have to find it out from the questions. What is the nature of the process? It's 27 degree. So essentially, the process, the constant temperature means this is the isothermal process. Okay, so for isothermal process, we know the formula. Okay, so what will be the B cross W? That is minus of PdV. Okay, so now if this is the minus of PdV, we have to find out the total work done. So then the work done will be integration of PdV. Let's say V1 to V2. This we have to find out. Now this is ideal gas. So you can write that P equals to RT by V. Why RT? Because this is for 1 mole. So it will be RTLN V2 by V1 with a negative sign. Now for ideal gas, we know P1 V1 equals to P2 V2. This is Boyle's law. So if you apply the Boyle's law, then we can write it RTLN P2 by P1, because V2 by V1 is essentially equals to P1 by P2 by V1 equal to P1 by P2. Yes. So then that minus sign is absorbed here. So RTLN P2 by P1. What is P2? 1 atm. What is P1? 10 atm. So you can write it minus RTLN 10. So just we have to now multiply R and T with ln 10. So it will be minus. Okay, what is the unit? This is ATM. So if it is ATM, then eventually ln 10 does not have any unit. But in the question, if you look at the option, in options, the unit is, let me check what was the option, calorie. And R is also given in calorie. So we have to use the calorie. So it is 2 into 2 calorie Kelvin inverse mole inverse into T. What is T here? 290, 27 means it is 300 Kelvin ln 10. So it is minus 2 into 300 into ln 10, and it will be calorie per mole. Okay, so if you calculate it, what will be the answer? Now 2 into 300 into ln 10, it is eventually be the minus of 138155 calorie per mole. So it is option B. Okay, so this question is not that much difficult. It's okay. So if there is any doubt regarding this and this is solved, then you can ask me. So this is easy, I think. So now the first second question is 1 mole of an ideal gas of that ideal gas CV is 2.5 R is allowed to expand. is allowed to expand at 300 Kelvin from 10 atm to 5 atm against an opposing pressure of 1 atm. After the expansion, the gas is heated at constant volume until the pressure just a second. The change in internal energy in joule will be okay. This question is tricky. I found because I tried once, but I did not able to solve it in one chance. So let me try it again. If it's solved, then it's okay. Otherwise, I'll solve in extras. Let me try it. Okay. So first, 1 mole of ideal gas is taken. It's allowed to expand from 300 Kelvin at 300 Kelvin means the first process A to B. Let's say this is isothermal because it's expand at a constant temperature 300 Kelvin from 10 atm to 5 atm. So A it was 10 atm pressure. It is expanded to B at 5 atm pressure. Okay, this is isothermal process. And then oh okay, against an opposing pressure of 180. That's okay. After after the expansion, the gas is heated at constant volume. Now it is heated. That means it's not isothermal process anymore. At a constant volume, it's isocoric process until the pressure becomes again 10 atm. So it's 10. Okay, becomes 10 atm. The change in internal energy. So first you have to understand that this process, the first process, this is isothermal. If it is isothermal process, so eventually del U for this process will be zero. We know that. For ideal gas, isothermal process, for in isothermal process, there is no change in internal energy. So du will be zero. So just we have to find out the du for this process, isocoric process. So now du is essentially d cross q plus d cross w. So it is d cross q minus p dv. Again, it's a isocoric process. That means volume is constant, so dv will be zero. So it is eventually d cross q. So d cross q you have to find out. Okay. Or we can write it. We know that this will be CVD. D cross q is eventually CVDT. So CV we know, DT we have to find out. So we have to just make integration. Let me do it in this way. So delta U will be CVDT and CV is constant. 2.5 R that is given. So DT we have to find out for TB to TC for this process. Okay, so TB and TC we have to find it out. Then we can eventually uh, do it. So this is just 2.5 R, then TC minus TB. Okay, so what is given in the question? Any temperature? Yes, this is 300 Kelvin. So TA is 300 Kelvin. So TB will be also 300 Kelvin. because we know this is isothermal, just we have to know the what is TC. TC we have to find out. Okay, TC we have to find out, then we can do. How we can find out TC? How we can find it out? TC. This is isocoric process. That means okay. So we can use the equation for ideal gas. The 3V equals to nRT for 1 mole RT. So we can write PB, PB equals to RTB, and again PC, VC, RTC. So here we can write PB by PB, PB, PB by TB equals to TC, VC by TC. Okay. And this VB and VC, this is isocoric process. So VB and VC should be equals to same. So we can cancel it out. So from here we can write TB by TB equals to TC by TC. So TC will be TC by PB into TB. So now we know everything. What is PC? 10 atm. What is PB? 5 atm. So PC by PB will be 10 by 5, and the TB we know. What is TB? 300 Kelvin. So it should be 150 Kelvin. No, 600 Kelvin, sorry. So 600 Kelvin. Now the del U will be 2.5 bar into 600 minus 300 Kelvin. So it is 2.5 R into 300 Kelvin. So it will be in Joule. So I should use 8.314 into 300. Okay. So it will be 2.5 into 8.314 into 300. So it is, okay, Joule. Okay. So answer is matching. Okay, it's not missing. So it is option D. Okay. So you have to visualize the overall process in two ways. Just we have to notice few things here, that for the first process, that is isothermal process. And for the isothermal process, the temperature is constant. And as the temperature is constant, so internal energy will also be constant because it's an ideal gas. It's an ideal gas. So D will be 0. But for the second process, that is isocoric process. And for the isocoric process, the volume is constant. And for this process, the internal energy will change. So we have to find out that the internal energy change for the isocoric process, the second one. So that we can eventually calculate, that it will equal to CVDT, and we can. And here we have to be careful that we have to use the ideal gas equation. Then only we can find it out. Let me see. Okay. So now the third question. Third question. Okay, so audio visual is fluctuating. We can. Now is it visible clearly? Now is it visible? Still, it is fluctuating. Am I audible? Yeah, maybe network issue. Okay, let me join again. So now you can hear me?
Yes, sir.
Okay. Let me cancel. And now is it visible?
Yes, sir. It is okay.
Okay. So for the question number 3. Okay. Third question. 1 mole of an ideal monatomic gas is allowed to expand isothermally at 300 Kelvin from 1 atm to 0.1 atm. Okay. First one is reversibly and second time it's irreversibly. So now they have asked to find out del G. So del G for processes. So now first let us considering that how we can find out del G. We know dg equal to VDP minus SDP. For isothermal process, it will be 0. So it will be just VDP. So dg will be VDP. Del G will be integration of VDP from P1 to P2. Okay. P1 to P2 we know. And V is if it is yeah, if it is a reversible process, so it is clear that we can write it. V is basically RT by P dP. Why RT? Because again it's a 1 mole. It's an okay, so it is RT ln P2 by P1. Okay, so what is P2 and what is P1? P2 is 0.1 and P1 is 1. So it is RTLN 0.1 or minus RTLN 10. So you can write it. Now, so delta G will be what is R? Again, it is asked in kilojoule. So again, we have to use 8.314. What is T? That is 300 eventually. And ln 10. So that will be del G. If you multiply, then what will you get? That 8.314 into ln 10 into 300. So it is minus 576,106 joule. So it is 5.761 kilojoule. Ah, so approximately we can use 5.74 for both the if you look at the option. So now this is for reversible. So here there is a very beautiful concept tree, you can say like this. It's what they have wanted to calculate the del G. Del G means eventually G2 minus G1, and we know G, Gibbs free energy, is a state function. So we know that for uh, state function is totally path independent. So it means that del G or del G or del G reversible should be equals to del G irreversible. So for both cases, the change in Gibbs free energy will be the same. So the answer will be minus 0.54 minus 5.74 minus 5.74 for both cases. So it is option A. So this is the third question. Now the fourth one. Okay, the fourth question I have few a problem in fourth question. So I'll solve it next day. I tried, but it was not trivial. So let me go to the question number 5. So question number 5 is saying that 1 mole of an ideal gas. This is again very straightforward. Tricky question. This is purely a tricky question. Gas at 2 atm pressure expands irreversibly and adiabatically into vacuum into vacuum to decrease pressure to 1 atm. The change in entropy. Okay. In joule per Kelvin. Okay. So again, an ideal gas that is expanding from 2 atm into 1 atm. Okay. Now they have asked to find out the change in entropy. So first, this is irreversibly and gravitationally. So let's say the process is like A to B. So now the entropy change will be del S equal to SB minus SA. Again, we know that S is a state function. That means entropy is a state function. So whether it is it reversible or irreversible, that does not matter. Del S will be the same. for the changing state from A to B. So it may be reversible, it may be irreversible. That will make any that will not make any effect. So SB minus SA. So that is equals to S reversible, del S reversible, or del S irreversible. That is the same. Now del S reversible, we know that is B cross Q reversible by T. Okay, we know. But they have mentioned the process is adiabatically. Adiabatically means we know for adiabatic process d cross q is 0, d cross q reversible is 0. So eventually del S reversible will be 0. So if del S reversible will be 0, then del S irreversible will also be the 0. So in this case, the answer will be 0. So no entropy will be changed. So option C. Okay. So this is totally a conceptual question. Now the question number 6. What is okay? This is very tricky question again. That they have asked del CV, del V at constant temperature. Okay, what it will be. We know that CV equals to the definition of CV is actually this is the heat capacity at constant volume. Heat capacity means the amount of heat needed to increase the temperature by 1 degree. So D cross Q by P at constant volume. This is our CV by definition. Now we know for D cross Q is essentially TDS. So we can write it because instead of D cross Q, you can write it T ds dt at constant volume. Okay, just instead of D cross Q, I have written that um, TDS. So it T is kept outside T ds dt at constant volume. So you can write it. So now, so what they have asked del CV del V at constant temperature. So it is eventually okay. Let me do it explicitly. That means del V of E into del S del T at constant temperature. Here it is. Temperature is constant, so we can keep it out. So del V into del S del T V del T. Okay. So now we know the Maxwell equations. So this superpower television trick. This is our Maxwell equation. So we have to find out del S del T V. But if you look at, there is no del S del T V combination. Means that these essentially need S to T to V. There is no S to T to V. So we can't use the Maxwell relation here. So how we can approach this? We know again that let me change the color. We know again that S is entropy is state function, right? Again. So if it is state function, then it will that means that it is S is exact differential. Okay. If S is an exact differential, so it will follow the Euler's theorem. So if Euler's theorem is followed, what we know? For Euler's theorem, d2z dx dy is equals to d2z dy dx, right? So if you write it explicitly, it means that ddx of dz dy at constant x this equals to ddy of this. So for entropy is basically a function of, from here we can write it, volume and temperature. So just analogously you can write del, it should not be day, it is not b, it should be del because it's partial derivative. You should be careful. These are partial derivative, okay? Okay. So we can write it now. Similarly, del v, del s, del t at constant v, now temperature, equals to del t, del s, del v t, this one we can write. So here what we have, del v, del s, del t v t, this one. So we can safely use this relation and we can write that. So del c v, so del c v, del v t is equals to, using this, t into del t of del s del v t at v. Now if you use the Maxwell relation, if you look at the Maxwell square, now del s del v t is there. It means we need s to v to t. So del s del v t is there. So for Maxwell square we know del s del v t is equals to del p del t v. Correct? So we know how to use it. Del s del v t is equals to del p del t v. So if you put it here, this relation, then it will be, then it will be p into del t del p del t v. Again it's b. So it is eventually del t2 at v. So this is the option B. So it's a very, very important question. It was a good question. Okay, we have to use this Euler's theorem. Otherwise, we can't find it out. Okay, so now question number 7. The fugacity of ammonia in stream gas. Of that gas, B is given. B is the Van der Waals constant, gas constant. A and B are the Van der Waals gas constant. This is liter mole inverse. Okay, at 25 degrees centigrade, having a true pressure of 10 atmosphere. True pressure we know, so we have to find out the fugacity. Okay, so now this is a ammonia gas. So there was two things, when the attraction is dominate, when the attraction will dominate and when the repulsion is dominate, we discuss, right? So but here only B is given. So if you remember, when the attraction is dominating, in that case, if you look at the Van der Waals equation, this is like this, right? This is the Van der Waals equation. So when the attraction is dominating, we are ignoring this part, as V, and when the repulsion is dominating, then This part was omitted. But now here, considering this equation, we can't reach a final form. So a final form, if you remember overall derivation. So only if you use this form, then there is a final expression of fugacity is there. That's why we have to always, for a numerical problem, always you have to use that form, which says that fugacity F will be P into to the power PB by RT. If you know that, if you remember the derivation, so this was, we also derived this formula where P is the pressure and F is the fugacity. So now just using this formula, you can direct solve it. What will be the P is given 10 ATM, B is the, so first we have to now calculate PB by RT. What is P? 10 ATM. What is B? B is 3.707 liter mole inverse. What will be the R? It's liter ATM. So 0.082 liter ATM, liter inverse ATM inverse only. And T is 25 equals to 98 Kelvin. No, it's liter, it's ATM, Kelvin inverse. Yes, this is the formula. Okay, so now if you use ATM, ATM will cancel out, liter, liter cancel out, Kelvin, Kelvin cancel out. So mole inverse will be there. This is for 1 mole, so that's why mole inverse will be there. So it will be, what would be the value? 10 into 10 divided by 298 into 3.707.082. So it is 1.517, a unitless value because it's in exponential. So F will be 10 ATM into to the power 1.517. Only there, one mistake. Let me check. Option is not matching. Okay, okay, okay. There is a 10 to the power minus 2. This 10 to the power minus 2 is there. I did not account that. So it will be 10. So it is eventually 10 to the power minus will be there, and it is 0.015. So now taking exponential, it is 1.015. So it is, if we multiply the, then it is 10.15285. So it is very close to option A. Okay. Now the question number 8. Okay, this question number 8, I think there is some problem in this question regarding the units, because if you look at the provided option, provided information that G is given. G is basically the gravitational acceleration, the gravitational force, 9.8 meter per second square. That is not anyway, I don't find how to use it, but the question is correct, but I think regarding the units, there is a problem. Okay, so that's why I'm not discussing question number 8 right now. So the answer is coming out, but still the unit is not very clear. If you look at the unit of that slope, del P del T, the del P del T slope is given as kg centimeter square mole inverse. Del P del T, the unit of del P del T is 40.5 kg centimeter to the power minus 2 mole inverse. That is given. But if you look, the unit of del P del T should be unit of the pressure divided by unit of temperature. So what is the unit of pressure? Newton per meter, and unit of temperature is Kelvin. So Newton is basically kg meter second per minus 2, and here it is it's meter square, and Kelvin. So the unit should be kg meter inverse second to the power minus 2 into Kelvin inverse. This unit should be, but the unit is given kg centimeter square, we understand, but second is not there. Mole is for 1 mole, that's okay, but Kelvin is not there, that is not accounted. So del P del T, the unit is not correct. Overall in question, I found that it's my opinion, the unit is not correct. But let me check again. Then if it is correct, then I will discuss in S plus. If it is wrong, then the probable correct form I will discuss. Okay. So for the numerical values are correct because the options, the answer is coming out that is matching with option. Some C or D, I forget, but still. Question number 9. The volume change in a phase transition is 0. Okay. Draw the pressure temperature curve of this type of phase boundary. Okay. So if you remember any phase diagram, let me draw it for the water. What does it mean? Phase diagram is pressure versus temperature diagram. So for water, how it was look like this, right? This region was solid, this region was liquid, this region was gas. These lines are essentially indicating the phase boundaries. This line is phase boundaries between solid and liquid. This is basically liquid and gas, and this is basically solid and gas. So these lines are representing the phase boundaries or the phase transitions. Phase transitions. So here, if you look at uh, how this slope of phase transition can be determined. Here they said that the volume change in a phase transition is 0. So that means, let's say phase is changing from A to B, any phase. We don't know whether it is solid, liquid, gas, uh, mm, mm, what kind of species is this, we don't know. But A to B, this is happening, and VA is almost comparable to VB. So this is basically a liquid gas because, sorry, solid liquid transition, because in case of solid liquid, the volume change tends to 0. But they have said that this is exactly 0. That means this is total equals. So del V, VB minus VA, it is 0. That is given. Means they have asked to draw the phase boundary. Uh, hmm, Pressure temperature curve of this type of phase boundary. So if that del V is 0, how this type of uh, curve, nature of the curve determined using the, we know, Clausius equation. For phase transition, that we use the Clausius equation, which is del P del T equal to del E by T del P. Correct? as we argued, we know when for water that del V is basically for water V liquid is less than V solid. That's why VL minus VS is less than 0. That's why the slope is negative. That's why the slope is negative. But for carbon dioxide, the slope is like this, positive, because most of the cases, most of the species, that volume of the liquid is greater than the volume of the solid. That's why the slope is greater than 1, positive slope, not greater than 1, greater than 0. But here they have said that the del P is 0. So if del P is 0, so essentially del P is undefined, or we can think like that it is approaching to infinite, infinite slope. So when, or undefined, better to take this. Okay. So now if the slope is undefined, if the slope is undefined, let me use del P del T. Del P del T is the slope of the pressure temperature pressure temperature plot. In pressure temperature plot, del P del T is slope. So we know slope is m. M is tan theta, correct? So tan theta, so we can write it that theta equals to tan inverse dp dt. So it is tan inverse del h by t del p. So it should be pi by 2. Okay, so slope is pi by 2. So in that case, if slope is pi by 2, then in pressure temperature curve, how it will look like? It will be like this. Okay, pi by 2 means slope, the angle with the x-axis, how the slope is measured. This angle is pi by 2. Okay. So this will be the, this is parallel to the y-axis or pressure axis. Okay. Question number 10. The parameter which always decreases during a spontaneous process. Spontaneous. Okay. At constant entropy and volume is. So they have asked to find out the parameters which is always be decreasing for a spontaneous process at constant entropy and volume. So how we can identify this? There is a trick. I have also mentioned that, but still let us do. We know for any spontaneous process, del S should be greater than 0. So we can write it like that. Spontaneous process essentially means the irreversible one, right? We have discussed these things. So del S reversible is 0. Okay, okay, let me write it like this. So del S for any spontaneous process, so del S should be greater than 0. Okay. Or we can write, if this is the case for spontaneous process, del is greater than 0. So again we know what we know, that du because q minus pdv, that means tds minus pdv, right? But these equations are valid for uh, non-spontaneous process basically. Okay, so from here what we can say that if ds is greater than 0, so we can write it. Let me how we can write that. Hence it should be du at constant entropy and volume, it is 0. From here we can see that this equation is valid for a reversible process, or we can say reversible process. For this is valid for reversible process. But now we have to deal with spontaneous process or irreversible process. Okay, so now the entropy for the spontaneous process is greater than 0. Entropy change for a spontaneous process. So now how we can do that? Here we have to put it there. This is for now del u spontaneous. You can write it. So it will be a spontaneous, or we can like this. So if ds is greater than 0 for spontaneous process, so du should be less than 0, right? So then only it will occur, because for spontaneous process it is for reversible process it is 0. So now for spontaneous process ds should be greater than 0. To make ds positive, du should be less than 0 for yes. So that means for spontaneous process, yes, it's correct. We can write du is less than tds minus pdv, or in general we can write in general du is less equals to tds minus pdv, where equality means the reversible process and inequality, the less than sign, refers to the spontaneous process. So here we can write that then del u sb okay. So this is the case. So this will be always negative. But there is a trick. We don't need to do all these steps again and again. We know our Maxwell square. This is very important trick. This square trick. So how we can write it? Directly seeing the square, u is connected with s and v. So du sv should be less than 0. H is connected with s and t. So del h s and p should be less than 0 for spontaneous processes. Del g p and t should be less than 0, and dA vt should be less than 0 in general. So this is a trick. Okay. So now the question number 11, the last question. Triple point of substances A, B, C, and D are. There are four substances: 0.2, 0.4, 0.8, and 1.2 bar respectively. The substance which sublimes under standard condition on increasing temperature is. Okay, so there are four substances. Okay, A, B, C, D. and the triple point of all substances are given, and they have asked to know a standard condition STP, uh, which substance will sublimes. Okay. So if you look at what phase diagram again for any substance, let's say for what, this is phase diagram of water, or in general, I should write like this, draw like this, yes. So this is solid, this is liquid, this is gas. Now this transition, solid to liquid, this transition is melting, or the reverse one is fusion. This is liquid gas, liquid to gas. This liquid to gas is boiling, and solid to gas is sublimes. So they want to know which species will sublime. So this is the triple point. This point, let's say O. This is the triple point. So when this is the corresponding pressure and temperature for triple point. Okay. So now if you look at below the corresponding pressure of triple point, let's say if you choose any point below that, here. So under this condition, if you go from if you increase the temperature, what does it mean? This curve means that if you increase the temperature of a solid, it will melt to a liquid. Again, if you increase the temperature, if you increase the temperature, let me draw like this. Again, you increase the temperature, then it will be boiled from liquid to gas. We know, but this is true. On increasing temperature, solid converted to liquid and liquid converted to gas. This is true above of the triple point. If you look at below of the triple point pressure, below of the PT, if you increase the temperature of solid, it will be sublimes to gas. There is no concept of liquid. Below PT, we can't have liquid. So that's why it will sublimes. So essentially, um, now the triple point for A, the triple point is given. The pressure is given 0.2. That means PT are given. PTs are given. Okay. For A, it is 0.2. For B, it is 0.4. For C, it is 0.8. And for D, it is 1.2. So now if you draw, um, so essentially from here, from this phase diagram, what we can conclude that directly, if pressure PT, any pressure P is greater than PT, it will not be sublime. It will not. If it is less than PT, then it will sublime. Correct? Now PT is given, PT is given, and what is the T? T is basically our standard pressure. They have asked. That is 1 atm. So PT for A is less than T. Okay. PT for B is less than T. PT for C is also less than T. If you do, these are, this is actually PTA, PTB, PTD, PTC. So for each cases, but for sublimes, what condition we need? We need that P is greater than PT. That means PT should be less than P. Then only it will sublimes. This is we can't achieve. But for the D, PTD is essentially less than P. What we have written? PT should be greater than P. For sublime, PT should be greater than P. So for this case, PT is 2.1.2, it's greater than P. That means B will sublimes at a station. Okay. So like no question is left now. So two questions I intentionally did not solve in this class. One question number four. In question number four, I have to look it again. Probably there is some trick maybe there. Or and in question number eight. Question number eight is there is dispute in units, so I have to fix it. In question number four, I will look it again. So these two questions I will solve in next class. So in this class, let me stop here. If you have any further question, you can ask me regarding today's discussion and also the discussion, the questions I solved previously in starting in the first half in that regarding the Debye-Hückel limiting loss in the ionic strength. So let me stop, and if you have any question, you can ask me.
No, sir, today. Thank you, sir.
Okay, so this question you send me, this question are clear to you now?
Yes, sir. I have to go through once again for
Okay, you will go
some
through
network
once again.
disturbance.
And again, if you have any doubt regarding the among this question or the question added in the next assignments as well, then you can also send me, and I will also discuss that in next class. And these two questions I left, these 4 and 8, these will also be discussed. Okay.
Thank you, sir. Thank you.
Okay. So now let me stop sharing.